Hello everyone, today we are going to learn the weakly supervised model in the custom deep learning classification. The fully supervised model introduced to you in the previous section requires complete labeling of the training samples, which means that each point involved in the training needs an explicit class label. This model is actually more costly for upfront data labeling. Then, in order to reduce the cost of upfront sample labeling while obtaining a classification model with comparable accuracy as possible, the MLS software provides custom point cloud training in a weakly supervised mode, which achieves higher accuracy classification by labeling a small number of samples. The custom deep learning classification function of this mode has the effect of reducing cost and increasing efficiency for point cloud classification tasks with large classification targets and fewer classification categories. The overall process is similar to the fully supervised model in that it requires 3 steps: sample labeling, model training, and data inference. The pre-software environment facilities and computer configuration can be referred to the video of custom deep learning classification in fully supervised mode. Here we focus on how to label the training data used for weak supervision. It is still through the manual edit category function inside the classification module and the manual category function inside the profile module. There are several broad principles of data labeling. Detailed subdivision of the object is not necessary during labeling. Only a portion of the points for each object needs to be labeled. The labeled points should be evenly and uniformly distributed in the target object. Label-less point cloud is allowed, but mislabeling or overlabeling should be avoided. When 2 objects are adjacent or have overlapping areas, both objects should have some labeled points. The class with the smallest label index in the labeled data will be ignored during training. Therefore, at least one of the never classified or unclassified points should be present in each LiDAR data. Each object in the scene should have labeled points as much as possible. Only 1% of the points can be labeled. After the point cloud is labeled, you first need to activate the Prepare Point Cloud Training Data function, and then add the corresponding data in the Training Point Cloud and Validation Point Cloud, respectively. Parameter introduction refers to the tutorial video of full supervision mode. Similarly, the default setting of the corresponding parameter is sufficient. If you have specific settings for a parameter, you can set the corresponding parameter value according to your needs. Then click Next. Check the ignored category information according to your needs and keep the desired category. For example, if 11 class labels are labeled, but a few classes are not involved in the classification training anymore, please check off this class. Select the folder where the data is saved. After clicking OK, the software starts to pre-process the data according to the settings. After the preparation of data is completed, the training data needs to be prepared. Activate the Train Point Cloud Classification Model function. Here, the trained file is selected as the training data. The features involved in the training are selected, and all the features contained in the data are checked by default. Features that are not checked in the data preparation will be grayed out. The processing mode only supports GPU for training. Select our weakly supervised point cloud semantic segmentation model. The fully supervised model has lower accuracy and slower training and inference. The batch size refers to the number of data inputs during each training iteration. Its upper limit is determined by the size of the graphics memory. Different graphics memory sizes have different recommended batch sizes, as shown in the figure. The maximum number of epochs needs to be adjusted based on the trends in loss and/or intersection over union. The best value is when the loss stops decreasing and the IOU stops increasing. From experience, we recommend 100 batches. Finally, choose the output path for the model. After clicking Next, go to the training interface. The progress bar of the training process is displayed at the top of the interface, and the training log is displayed in the box below. Click Start to begin the training. During the training process, Analyze the changes in the curves to observe the training status. Normally, the loss will decrease as epoch increases and stabilize after tens or hundreds of epoch. The MACC value will increase as the epoch increases and eventually stabilize. The MIOU will gradually increase and stabilize starting from a certain epoch. If the trends of the three curves do not conform to the aforementioned characteristics or the curves oscillate, it indicates that there are problems with the training, such as inconsistent annotations or very poor annotation accuracy in the training data. After the training is completed, you can click Export Report to view the training report results. The report file will automatically be saved in the project file. The trained model is saved in the model folder. You can copy this folder to another computer with an NVIDIA graphics card and use it for inference in the LiDAR360 MLS software. The computer used for inference also needs to meet the basic configuration requirements. Finally, for model inference, activate the Classify Point Cloud using Trained Model function with the trained model. Then add the point cloud data to be classified. The settings for block length, buffer, and batch size should be consistent with the setting during training. Choose a model path as trained model file with a high quality such as max IOU val.pb. If you are interested in a specific category, it is recommended to choose the file corresponding to the epoch with the maximum IOU for that category according to the training report. The log path can be left as default. Click Next to go to the inference interface, where the progress bar and log window are displayed from top to bottom. Click Start to start the inference. After the inference is completed, the selected .light data file will be replaced. After reopening the inferred point cloud, you can see the effect of the weakly supervised model. We can find that all points actually participate in the prediction process, and some points that should not be classified are also assigned to the annotated category. In this case, activate the function for classifying by attributes. Select all the classified categories on the right side. Choose any target category. Switch to additional attributes. Select pred after the attribute. Set the minimum value to 0.195 and the maximum value to 0.4. And click OK to assign the points that do not belong to these target categories to another category. Finally, let's take a look at the classification results of the same dataset using both supervised and weakly supervised models. The classification results for some major categories such as buildings, vegetation, and ground are similar, although the weakly supervised model can reduce the initial sample annotation. It still has limitations in classifying details and small targets. At the same time, the result of the weakly supervised models can be used as initial data for fully supervised sample annotation, which can improve the efficiency of the fully supervised data annotation to some extent. Therefore, it is necessary to choose the appropriate model based on different classification tasks. This is the introduction of the custom deep learning classification functions. Thank you for watching.